Hi, welcome to our e-lecture on the topic of scheduling. In this chapter, we're going to be studying or learning these three main objectives. Firstly, we're going to understand how an operating system performs scheduling. We're going to review important concepts like deadlocks and re-entry functions and understand how we can actually avoid a deadlock situation. Okay, so from what we have learned so far about multi-threaded programming, we know that with a single CPU in the system, only one thread can be running at any point of time. Okay, which means the rest of the threads must be waiting for their turn to make use of the CPU. Okay, and the person in charge of managing this is actually the scheduler. Okay, so the scheduler actually looks at the multiple waiting threads, okay, and selects one of these threads to uh, make use of the CPU and run, okay, while the rest of the threads will be waiting. Okay, so if you look at the thread states, okay, what you have is at the initial sort of glance, what you can probably see is the threads that are waiting for a chance to run will be in the ready state. And once the scheduler chooses one of these tasks to run, it will transition over to the running state. Okay, and of course, if I have not yet created the task, okay, that means it is considered inactive. Okay, and it's not known to the scheduler. Okay, one of the, of course, common type of scheduling which we know is what we call the time slice scheduling or round robin sequence. Okay, where each thread basically runs for a fixed amount of time. Okay, and once it reaches the end of its allocated time, it basically gives up its control of the CPU to the next thread that is waiting in the sequence. Okay, so that's what we generally call as the round robin sequence. Okay, it may be an appropriate strategy for some types of applications. Okay, so for example, okay, if I say it's just a simple remote control system, okay, that does not require any immediate response, okay, in terms of timing. Okay, so in those kind of applications, this may be a suitable scheduling strategy. Okay, but of course, when you talk about real-time systems, okay, they require a kernel, okay, that is much more responsive, okay, to external events. Okay, so you cannot have a time slice scheduling approach to a system that requires real-time response. Okay, okay, so another thing that we also need to know about is uh, besides the ready and running, there could be cases where threads are waiting for an event to occur, okay, or for some shared resource to become available. Okay, it could be a situation where the thread is waiting, okay, for a shared resource, okay, but it is not yet available. Okay, so it cannot run until that resource is it acquires it. Okay, so during this time, of course, the scheduler should choose another thread to run. Okay, while the one that may have been selected has to wait. Okay, and in that situation, what do you do with the delayed task? If I just move it back into the ready queue, okay, then it is quite an inefficient way of handling it, because if I move it back to the ready queue, then uh, again, when the scheduler schedules it to run, it may realize that it doesn't have the resources that it needs. Okay, so again, it will go back to the queue and join it again. Okay, so this adds a lot of unnecessary switching overhead. Okay, so what is the solution to this? Is basically to add another state which we call the pending state. Okay, so a pending state basically means that a thread is waiting, okay, for an external event or some shared resource to be available. Then it will transition to the ready state. Okay, so once it gets that resource that it was waiting for, it will be able to transition from the pending to the ready state, and from there the scheduler will then look at all the currently thread, or all the current threads that are in the ready queue, and select one of them to transition to the running state. Okay, so that is basically how the threads sort of switch around, okay, between the different states. Now, uh, so there's now we're going to look at this context switch. Okay, context switch, as we have seen before, is basically what happens when a task is running and you need to switch out that task from the CPU to allow another task to take over the CPU. Okay, Now let's look at this situation which we have, which is a non-preemptive. Okay, so both task A and task B are in the system, and currently task A is running. Okay, when task A is running, okay, uh, what happens is there's an interrupt service, there's an interrupt that is triggered. Okay, so this is an interrupt that is captured by the system, and once you capture the interrupt, you jump to the ISR. Okay, and in the ISR, what we are doing is we are doing a post. Okay, so in this situation, you can think of it that maybe thread B actually wanted to have a OS SAMPAN. Okay, so I'll just give you an example, okay, of a resource. So it could have been that it could have requested for a semaphore and it was not available, so it went to a pending state or block state. And the ISR, once it ran at some point of time in the ISR, it posted the semaphore. Okay, so you got to call OS SAM post. So once the SAM post is called, which means that thread B, which was waiting for the semaphore, now has acquired the semaphore, and so it will transition from the pending state to the ready state. Okay, then what happens when the ISR completes? Okay, it will resume back to thread A, and thread A runs. Okay, and eventually, since this is non-preemptive, so it will voluntarily give up the CPU. So when you say yield, means you are voluntarily giving up the CPU. And once that happens, then thread B will get a chance to run. Okay, so this is what we call a non-preemptive context switch. Okay, so a thread A is running, and though an interrupt unblocks thread B uh, can transition to ready state, but it will still wait until thread A gives up the CPU, then it will run. Okay, so this is basically the explanation, okay, based on what I said just now. Okay, so basically for a non-preemptive context switch, okay, you need to call the yield function so that you basically move the current thread to the ready state, and you invoke the scheduler, okay, that will eventually select the next thread to run. Okay, and of course, besides yield, there are of course other types of kernel calls that can also invoke the scheduler to come into action. So one could be to terminate the thread, okay, to wait for an external event to occur, okay, to wait for a shared resource that is currently in use, or to sleep for a specified amount of time. Okay, so some of these examples we have actually seen in the earlier uh, lecture slides, okay, and of course in the demo of the OS code, okay, in situations where we were using the message queues, okay, or task queue and semaphores. Okay, so these are all situations where you are waiting for some external event to occur or for a shared resource to be available, okay, before you are actually going to proceed on. Okay, so for a non-preemptive thread state, basically what you have is when a process is running, okay, when a process is running, if it tries to acquire a resource and is unable to get the resource, it will go to a pending state. So pending is equivalent to a block state. Okay, once that resource is available, it will transition to ready, and then from ready it can go to running. The other way is from running, I can voluntarily call yield. Okay, so when I voluntarily call yield, I am actually giving up the CPU, okay, on my own will, and I transition to the ready state. So I join the ready queue, the queue of tasks that are waiting for their turn. Okay, and then I can transition to run at some point of time. Of course, while you're running, you can also be interrupted. Okay, when the interrupt is triggered, you jump to the ISR and then you come back. Okay, so of course, the inactive state we don't really worry too much. It's basically the state that you have when you are not yet, or when you're not visible to the scheduler. Okay, but for now, we don't need to worry about it. We just assume that the moment I create a task, it's always transitioning between the ready state, block state, and running state. In preemptive context switching, okay, what really happens is a bit different from what we saw just now. Okay, so assuming now we have the same two tasks, task A and task B, okay, and in this situation, again from this time, which we'll say at time t equals to 0, prior to that, we can say that maybe thread B tried to do a OS SAMPAN, okay, and it was not able to get the semaphore, so it went into a blocking state. Okay, so task A is running, okay, and at some point of time there is an interrupt. Okay, there's an interrupt, and because of the interrupt, you jump to the ISR, and in the ISR there is a pause of the semaphore. And so when there is a pause of the semaphore, what happens? That means task B, which was waiting for the semaphore, will now acquire the semaphore and will be allowed to transition from the pending state to the ready state. Okay, and if task B was a higher priority than task A, okay, if task A is high priority and task B is high priority and task A is low priority, then what would happen at this point of time is, once I complete ISR, since the higher priority task B is in the ready state, that task will then be scheduled to run. Okay, so task A would be after the ISR, task A would actually go into the ready state, okay, and not the run state. So that is a big difference between preemptive and non-preemptive. In non-preemptive, what we saw is after you finish, even though you released a resource and made another task uh, become unblocked and go to the ready state, you still go back to the original task and you wait until you voluntarily give up the CPU, correct? You call the yield function, then the context switch happen. But in a preemptive system, what happens is, the moment a higher priority task becomes ready, it will automatically be selected to take over the CPU and run. Okay, so that is the big difference between non-preemptive and preemptive. Okay, and that is actually very critical, because that behavior is actually what gives us the real-time response capability that we want in a RTOS based system. Okay, so that is so this slides are to just explain what I mentioned just now. So in a preemptive kernel, the thread states are a bit different. When I'm running, okay, if I try to acquire a resource and I don't get it, I go to the pending state, which is the equivalent of a block state. And of course, once I get the resource that I was waiting for, I will transition to the ready state. Okay, and after that, when I am selected to run based on the priority, I will then switch over to the running state. Okay, similarly, if I'm interrupted, after I service the interrupt service routine, I may go back to running or I may go to ready, depending on what happens in the ISR. Okay, so that is basically how a preemptive kernel works. Okay, and as you can see in a preemptive based system, the priority is very important. Okay, so there's two types or two manners in which you can assign priorities. One is called static, okay, which means they are fixed and do not change at all during the entire execution. And the other is what we call dynamic. Okay, in dynamic, okay, the priority of a task may change in runtime or during runtime. Okay, and this is to avoid a priority inversion problem. Okay, so what is a priority inversion problem? Okay, so imagine that there are two tasks that use the same resource, task A and task B. Okay, so so I have two tasks here. Okay, so A and B, and A is lower priority and B is higher priority. Okay, and a lower priority thread acquires resource A and is still holding on to it when it gets preempted. So let's assume that at time t equals to 0, okay, B was already in the block state. Okay, so it's going to carry on in the block state, okay, for a while. Okay, and A at time t equals 0 is running. Okay, so it's running, and during this time where it is running, at this point of time, it go and acquires resource A. Okay, and if after some time, okay, let's assume that I have a context switch over, and task B starts to run. Okay, task B starts to run, and at some point of time it tries to acquire again the same resource A. What would happen? It would be blocked. Okay, so this wouldn't be allowed. Yeah, it will go to a block state. So from here onwards, you will go to a block state. And once it goes to a block state, what does it mean? That means it needs to wait until task A resumes. So from here to here, task A was blocked. Okay, and after task B gets blocked, then task A gets a chance to run. Okay, task A gets a chance to run, and you have to wait until some point of time when task A finally releases the resource A. Okay, it releases resource A, then only you can have the context switch back to task B. Okay, so this is what you call a priority inversion problem, because you have a same resource, which is resource A, okay, and both of them are trying to, or both of them need to use the same resource, okay, but it just so happened that the lower priority task acquired it first, and when the higher priority task started to run and it tried to acquire it, at this point of time it wasn't able to get it. Okay, so it becomes blocked, and then you allow a lower priority task to run. Okay, and only when the lower priority task gives up that shared resource, then the higher priority task can resume. Okay, so this is what we call a priority inversion, because we have a situation where a low priority task is forced, we have a situation where a high priority task is forced to wait for a low priority task to complete some activity. Okay, so of course this is what we call a bounded priority inversion in this situation, because you only have two tasks. Okay, so this is basically what I mentioned just now. So you have a high priority task that was running, okay, and a low priority task. Okay, and if let's say the high priority task tries to acquire the resource that was already acquired by the low priority thread earlier on, okay, so sometime earlier you already have the low priority thread acquiring this resource, then what happens? Okay, when the high priority thread tries to acquire it, it becomes blocked, and so the low priority thread will run. Okay, only when you complete it, okay, and you release the resource, then your higher priority thread can resume. Okay, so you can see that this whole duration where a low priority thread is running, blocking a high priority thread, so that is what we call a priority inversion problem. Okay, of course there's also another more serious issue called unbounded priority inversion, because what if instead of just two tasks there is another third task that can preempt the lower priority thread? Okay, so coming back to this, what if I have a medium priority thread? Okay, and at this point of time, let's say at this point of time, the medium priority thread takes over and starts to run. Okay, and the medium priority thread can run for as long as it wants, and only after it finishes, okay, I can transition back to the lower priority thread to carry on running and then release the resource. So that can add significant amount of unpredictability to when the high priority thread will actually get a chance to get the resource and actually resume, okay, from where it left off. Okay, so that is what we call unbounded priority inversion. Okay, so how can we solve this issue? Okay, so the good thing is, what we want to do is we want to prevent the low priority thread from being preempted from a medium priority thread during the priority inversion. Okay, and there are two strategies in place. One is called the PIP, Priority Inheritance Protocol. The other is called PCP, Priority Ceiling Protocol. And both of them have the same technique, which is to manipulate the thread priorities during runtime. So let's look at the first one, Priority Inheritance Protocol. So in Priority Inheritance Protocol, what will happen is, okay, when a thread fails to lock a mutex, okay, the kernel looks for which thread owns the mutex. Okay, and what happens is, if the owner of the mutex is actually having a lower priority, then I will temporarily raise the priority to match that of the block thread. Okay, and why does this work? Because the moment I raise the priority to match the high priority thread, the medium priority thread is removed from the picture. Okay, so let me explain this again. So now this same scenario here, I have a medium priority thread here, high priority and low priority. So in priority inheritance protocol, what will happen is, at this point of time, where the high priority thread gets blocked because of a shared resource, the priority of this low priority thread will be raised to the same level as the high priority thread. Okay, which means what? Which means that this scenario here will not happen. Okay, because this scenario only happens because there is another thread that is higher priority than this low priority, but lower than the higher priority, correct? Okay, so because of this situation uh, will be avoided, okay, with the priority inheritance protocol, because the moment the block is detected by the OS, this thread's priority will automatically be raised to match the high priority thread's priority that is currently being blocked. Okay, so what will happen when the high priority thread gets blocked? I will make sure that the low priority thread actually gets to run until it releases the resource. Okay, of course, if there is something even higher priority, then of course the OS will switch to that. But assuming that there is no other higher priority thread, your lower priority thread will get to run until it completes and releases, or not say until it completes, but until it releases the resource. Then it will automatically come back down. So at this point of time, once it releases the resource, the priority of the thread will be then brought back to the original level. Okay, then the high priority thread can then resume from where it left off, okay, because the resource that it was blocked for, uh, it now gets it. Okay, so that is basically the priority inheritance protocol. Okay, and of course the good part is it is actually implemented in the OS kernel itself, so you do not need to worry about it. Okay, so as long as your OS kernel supports it, it is already built in and provided for you. The other protocol is what we call the PCP, the priority ceiling protocol. So in priority ceiling protocol, what happens is the priority of the low priority thread is raised immediately the moment it acquires a shared resource. Okay, and restored to its original value the moment it releases the resource. Okay, so coming back to the same picture, that means I do not wait for this event to occur. At some point of time earlier on, the resource was owned by the low priority thread, correct? So at that point of time, when the resource was owned by the low priority thread, I would have already raised it to match. Okay, so the moment the low priority thread tries to acquire a resource that is shared with the high priority thread, I will immediately raise it to the same level so that I do not have any situation where the high priority thread would be blocked, because the moment I finish, I will release, and if the high priority thread wants it, it will be able to get it after that. Okay, so that is priority ceiling protocol. So you raise it immediately the moment you have a situation where a shared resource is acquired. Okay, so this is basically the highest, the priority that it raised to is highest among all the threads that access the same resource. So that is why it's called a priority ceiling. Okay, so of course the disadvantage is it will always raise the priority. So even if the high priority thread is blocked or not, okay, regardless of that, it will always raise the priority, which means that it could potentially delay the execution of other medium priority threads unnecessarily. Okay, so that is of course one of the sort of drawbacks of the PCP. Okay, of course now when we look at this entire real-time kernel, we can see that assigning a priority to a task is actually a very, very important thing, because the whole dynamics of a real-time system is very much dependent on how we assign priorities to the various tasks. Okay, and this idea and this fulfillment of assigning priorities itself is a very, very delicate task. Okay, and what you need to do is you need to make sure that you assign priorities such that you are able to fulfill all the real-time performance requirements that you need. Okay, and of course when we say real-time, it doesn't mean we must compute every output as fast as possible, as long as you are able to do it within the deadline. Okay, so that is what is important. We must make sure that all outputs are computed and delivered before their deadlines. Okay, so that is the objective of assigning priorities. Okay, so how do we assign priority? So let's look at this approach here, which is deadline driven scheduling. So every task, okay, that you have actually has two timing parameters associated with it. One is what we call the minimum time required to compute the response. Okay, so depending on what the task is doing, how much time does it need to actually compute and give you a response, and the maximum time that is allowed by external constraints, which is the deadline. Okay, that means if I give you a task, okay, task A. Okay, let's say, and I take this amount of time to compute. Okay, that is the minimum. Okay, that if I run from start to the end without any preemption. Okay, but at the same time, we know that there could be a situation where I'm running and halfway I get preempted. Okay, and then after I get preempted, I need to resume again. Okay, so that is the maximum time, okay, that I am able to run within the deadline that I specify. So I must be able to specify some deadline. Okay, that once I start a task, I must complete it within a specific deadline. And what is the worst case scenario considering the fact that I could be preempted, okay, by other tasks or interrupts. Okay, so let's consider two tasks. One is a 2-second task with a deadline of 4 seconds. The other is a 4-second task with a deadline of 5 seconds. So which task should run first in order to ensure that both deadlines are met? Okay, so if I run the 2-second task first, what happens? I run it, okay, I complete before the deadline, okay, and then I start the next task. But when the next task runs, by the time it completes, the deadline would have been missed because the deadline was 5 seconds. Okay, the other approach, which is I choose the 4-second task first, then I complete it, okay, within the deadline, and then I start the 2-second task. So both the tasks can complete within the deadline. So as you can see, the approach of using the shortest deadline first actually is better in this case. Okay, so that brings us to one of the most popular scheduling strategies, okay, which is what we call rate monotonic scheduling. Okay, where of course for rate monotonic scheduling, we assume that all tasks are periodic in nature. Okay, so for this scenario, all we need to do is we look at the execution period, and tasks with the shortest execution period will be assigned the highest priorities. Okay, so the whole idea how RMS works is I assume that all tasks are periodic in nature, okay, and I look at the periodic intervals. So the logical approach is if a task has a very short period, that means high frequency task, okay, that means it needs to keep using the CPU at a very high rate. So I need to make sure that whenever it is ready, it should be able to run. So I will give it a higher priority. Okay, whereas tasks which have a lower period, okay, that means they only need occasional need of the CPU, I can give them a lower priority. Okay, so that is basically the logical thinking behind RMS, and is one of the most popular ways of analyzing a system, okay, to understand if the timing requirements and deadlines can be met. A deadlock is a situation where you have two or more threads, okay, being blocked, okay, waiting for each other's resources, okay, and it usually occurs whenever these threads require access to two or more shared resources simultaneously. So let's look at an example of how this can occur. In this example, we have two tasks, T1 and T2, and both of them require access to resource 1 and resource 2. Okay, and what do you see here? You can see that in this timeline, T1 runs first, and while it is running, it acquires resource 1. Okay, so it acquires resource 1, and after that, what happens is there is a context switch over. So I have a context switch over to T2, and while T2 is running, it goes and acquires resource 2. Okay, and after some time, it tries to acquire resource 1, okay, but it's not able to acquire resource 1, so it gets blocked. Okay, so it tries to acquire resource 1, it doesn't get it, it gets blocked. Okay, and since T2 goes to a block state, T1 can resume running, and when T1 resumes running, it runs, and at some point of time, it tries to acquire resource 2, and it doesn't get it because resource 2 was already acquired, okay, by T2. So this doesn't come through. So T1 gets blocked waiting for resource 2. So you can see that from this point onwards, okay, both the tasks will be waiting indefinitely for each other. Okay, neither one is giving up the other resource the other person wants. And this is basically what you call a deadlock situation. Okay. And of course this is just shown for two tasks for simplicity, and you can have a situation where multiple tasks, okay, can be waiting for multiple resources, okay, in a similar fashion, and all of them could be in a deadlock situation at the same time. Okay, so this is of course a serious issue, and of course fortunately for us, many development tools have progressed, okay, to a level where they are able to do some analysis of software and actually detect such situations and sort of warn us automatically while we are compiling and building the code. Okay, but of course it is still up to the programmer to find a solution to the problem. Okay, so how do we prevent deadlocks? Okay, there are two possible ways of approaching it. One way is we require all threads to acquire resources in the same order. Okay, so this will ensure that, okay, I make sure I follow the same order. So the moment the another task comes in and the first resource is already unavailable, you will not be able to proceed any further. Okay, so if I go back to this earlier example here, you can see that if task 2 had tried to require resource 1, so instead of resource 2, if task 2 had actually tried to acquire resource 1 and then it gets blocked, okay, what will happen? It will start to be in a block state from this point onwards. Okay, and eventually when T1 resumes, it will carry on and it will still be able to get the resource 2 and carry on, correct? And eventually when it uh, gives up both the resources, then only or when it gives up R1, then T2 will be able to resume. Okay, so that can help us to prevent a deadlock situation by enforcing an order in which you acquire resources that are shared across multiple processes. Okay, and of course another possible mechanism is if uh, you reach a situation where you are unable to acquire all the resources that you want, okay, you just release all the resources and you start over again. Okay, but of course this requires more thinking and more planning on how you want to go about doing this and what is the order in which you release the resources. Okay, another critical aspect of systems is the ability to ensure that in a situation where you are in a deadlock or something really bad happens, you want to be able to recover from the system. And what actually helps you to do it is this sort of peripheral block in your processor, which is what we call a watchdog timer. Okay, a system can fail due to many reasons. Okay, so of course what we saw just now is things like priority inversion, deadlocks. Okay, so these are what we saw just now. It could be a programming error, it could be some hardware failure, some unexpected event, a battery being drained unexpectedly, some sensor failing that your system is not unable to compensate for, and so on. Okay, so a system can fail for many reasons. Okay, and what we want is if the system is in the process of failing and reaching a state where it may not be able to recover. Okay, what we want is we want to be able to recover the system in a safe way. Okay, so that is where a watchdog timer comes in. Okay, and what does a watchdog timer do? It's basically a hardware counter that will keep on counting downwards, okay, towards zero at a fixed rate. Okay, and the software is expected to periodically reset or restart this counter so that it never reaches zero. Why? Because the moment it reaches zero, what it will do is it will actually reset the entire system. Okay, so the whole idea is if I'm able to keep running this code, okay, to periodically go and reset this watchdog timer, then the system is still functioning, so it's fine. But if I'm unable to do this, then I could be stuck somewhere, okay, in some deadlock situation where I'm unable to reset my watchdog timer. So I will have to reboot the whole system and make sure that I restart all over again. Okay, so in many safety critical applications, okay, you need to also of course make sure that before you reset everything, you have to put everything in a very safe mode before you reboot the system. Okay, so of course it at a theoretical level it is easy to understand, but to implement it you also need to put in a lot of thought into it, okay, to make sure that you want to make sure everything is in a fail-safe state before you actually go and reset the system. Because once the system resets, okay, you want to make sure that you boot up to a proper state where you can still carry on running. Okay, so that is um, the way you need to approach it. Okay, of course, watchdog timers may not necessarily be always effective in catching a deadlock situation or a situation where there is something wrong, because generally in most processor systems, the watchdog timer is implemented as a interrupt service routine. So periodically the interrupt service routine will trigger to update the timer. Okay, so even though there is a deadlock situation, or even though there is a priority inversion situation, it is still possible for the watchdog ISR to still function properly and carry on with making sure you do not have a system reset, okay, by uh, keep on updating the watchdog timer. So so the watchdog timer is good. It helps us in some cases, but it may not always be able to catch a system failure. Okay, so of course we need to look at other strategies, okay, that and those are beyond the scope of this module. Okay, another important thing for re-entrant functions. Okay, as we know, in a real-time operating system, context switching can happen anytime. Okay, so when a context switching is happening, okay, it could also happen while you are in the middle of a function call, which could be a shared function. Okay, so for example here, I enter a function store string, okay, and store string is maybe a common library function that many tasks may want to call. Okay, so what you want to do is you want to make sure that if I'm in the middle of a shared library or a shared function, okay, that is used across multiple tasks, those functions must be able to handle this ability to uh, not mess up or not corrupt any data that it is dealing with, okay, for the different functions that are calling it. Okay, so in order for us to make sure that a function is re-entrant, what we need to do is we must make sure we use thread specific instances of any data. That means they must be thread safe. Okay, how do you make sure they are thread safe? You only thread safe is actually automatically implied the moment you use only automatic variables or dynamic allocation variables within the function. Okay, that means when I jump into a function, okay, if I jump to a function and I declare a variable here, integer a, integer x, and so on, these are automatic variables. Or if I use a malloc function here, these are all automatic variables because they are created when I enter the function. The moment I exit the function, they effectively sort of disappear because they are on the stack. Okay, uh, so those kind of functions, okay, where you create variables only within the function space, those are automatic variables and those are thread safe. The kind of variables you need to be very careful about are those that are static or global, because if you have static objects or global variables, then those will always retain the value even after I exit the function. Okay, so if I declare a global variable integer x, again inside my function a, I'm going to make use of x in some way, then that is an issue, correct? Or if I declare another static variable here, static integer y, that is also an issue because these variables will hold on to their value even after I exit from the function. Okay, so when one thread is using it, it may hold some value, and then if I get preempted and another thread calls the same function, then it's holding on to data from another thread, okay, which may corrupt or may interfere with the way it is being used in the current thread. Okay, so that is what we need to be careful about. In order for me to say that a function is re-entrant, you have to make sure that they only use automatic variables or dynamically allocated variables. Okay, so we'll just look at some case studies here to understand how all of these things actually have played a part in the real world scenario. So in 1994, okay, a deep space probe called the Clementine, okay, was launched, okay, to the moon to make observations of the moon. Okay, and after a few months of operation, what happened was there was a software exception, okay, causing the thruster to fire for 11 minutes, okay, which depleted most of its fuel, okay, because it caused the probe to continuously rotate at a very high rate, okay. Though after a while, after this 11 minutes, they regained control, but it was too late because a lot of fuel was already lost, okay, so they couldn't really complete the mission, okay. So this example sort of shows you the severity of how a small software bug can actually cause a major catastrophe to the whole mission, okay. This is an example, okay. In 1997, the Mars Pathfinder, okay, what happened was there was a priority inversion situation where a high priority communication task, okay, high priority task was actually forced to wait because the mutex was held by a low priority science task. Okay, as you know, this kind of rovers on the moon, they are actually designed, okay, to maneuver around the terrain and conduct some experiments by collecting samples of the soil and so on, okay. So what happened in this situation was this low priority task, okay, which was doing this science experiment, okay, was actually blocking the communication task, okay. So as a result, the whole timing of the system was compromised, and luckily there was a watchdog timer that was able to detect it, okay, and it rebooted the system, okay. And of course, scientists were able to identify the problem and upload a new code to fix the problem, okay, and with that they were able to save the mission, okay. And another interesting issue here is the timing issue, okay. So as you can see here, during Operation Desert Shield, okay, the US military deployed the Patriot missile system, and what it does is it uses the velocity of its target and the current time to predict where the target will be from one instant to another, okay. So what happened was there was a bug in the targeting software where over time the clock would drift further and further from the accurate time, okay. So this is of course an issue because in many of our um, embedded systems, okay, where we make use of time, there will be some drift, okay, that can occur over time, and in most systems we may sort of ignore the drift, okay, and we may just recalibrate on our own. Let's take for example, you have a digital watch, you may say every few months or even a year that it drifts slightly by a few minutes, you just readjust it back, you don't really bother about it too much, okay. But in this case what happened was uh, the bug was known, okay, and what the developers sort of told the soldiers was all you need to do was to regularly reboot the system, okay, to make sure that you do not get affected by this drift. But again, this is a common problem of communication between a developer and the user, correct? When they said regularly reboot a system, there was no clear guideline on how to interpret this term regular, correct? And so what happened was the system was left on for more than 100 hours, okay. And what happened was incoming missile miscalculated to land in open field, okay, due to the drift of 0.34 seconds. So a missile was coming in, okay, and what this Patriot missile system did was while it was monitoring this incoming missile, it sort of gave a reading or a conclusion that it was supposed to land in open field because of this error, this drift. But actually it went to hit on a US airfield, killing many soldiers. Okay, so again, this is a very important issue as software developers, okay, that we want to make sure that uh, we communicate the requirements or the behavior of the system in a very clear manner to the end user, okay. So if it was very clearly communicated that, for example, you need to reboot the system every 24 hours, then that would have helped, and saved so many lives. Or of course another way to think of it is you can also choose to prompt the user to do a reboot after a certain time so that the user knows that it is time for a reboot, okay. So these are ways in which you could actually have improve the system, okay, to make it more user friendly and safe for the soldiers to use. Okay, so basically in this lecture we have looked at the several aspects of scheduling and task states, as well as looked at priorities, and also discussed deadlocks and reentrant functions. Okay, so that wraps up our whole discussion on OS and scheduling. Okay, so I hope with all of this you are well equipped, okay, with some very good foundations in OS. Okay, and the next topic would be on cache and memory. Okay, so look forward to the next lecture. Thank you.